Picture this. You're standing on the Giza Plateau about 45 centuries ago. No cranes, no engines, no trucks, no steel tools like we have today, and yet right in front of you a building is rising that still looks impossible. The Great Pyramid. At its original height, the Great Pyramid rose to about 146 meters, or 481 feet. It was the tallest human-made structure for thousands of years. Now here's the scale that really matters. More than 2,300,000 limestone and granite blocks were moved into place. The average block weighs about 2.3 metric tons, or about 2.5 tons. So if you spread 2.3 million blocks across 20 years, that averages roughly 315 blocks per day. Not by one person, by many crews, all day, every day, running a massive system. And here's another mind-blowing detail. The Great Pyramid is aligned to the cardinal directions with accuracy better than 4 minutes of arc. That's about 1/15 of 1 degree. So the real mystery is not, did they build it? We can see that they did. The mystery is, how did they move and place that much stone with that level of precision? Today we'll break down 5 major theories, just engineering, then end with what's most likely, a smart combination of methods. Theory number 1 is the simplest, the straight ramp. You build one long ramp out of packed earth, rubble, and mud brick leading up to the work level. Then teams haul blocks on wooden sleds up the slope. It makes sense early on. Ramps are simple, and ramps were used in ancient construction. But the straight ramp runs into one giant problem: geometry. If your ramp is too steep, pulling multi-ton blocks becomes risky and exhausting. So to keep a gentle slope, the ramp has to get longer and longer as the pyramid gets taller. By the upper levels, a straight ramp could become enormous, possibly demanding an extreme amount of extra material and labor. So a straight ramp might explain the early phase. But by itself, it's hard to imagine it reaching the top efficiently. Theory number 2, the zigzag ramp. Instead of one ramp going straight up, the ramp switches back and forth on a face of the pyramid, like a mountain trail. This shortens the total ramp length and keeps the slope manageable. But it creates a practical issue: turning. Turning a heavy block on a sled is not easy. Every corner costs time, space, and control. And the higher you go, the tighter those working areas become. Also, ramps pressed against the outer face can block the builder's view of the pyramid's geometry. And precision matters here. So zigzag ramps could be part of the solution, especially in the middle stages. But they don't answer everything. Theory number 3 is the famous one, the spiral ramp. In this model, a ramp wraps around the pyramid like a corkscrew, spiraling upward. The advantage is obvious. The ramp stays close to the pyramid instead of stretching far into the desert. But it comes with trade-offs. An external spiral ramp can block the edges and corners, and those are key reference lines for alignment. And tight turns are still a challenge for multi-ton loads. So the spiral ramp looks great in diagrams, but as the only method, it raises questions. Theory number 4 is one of the most discussed today, the internal ramp. Instead of building a massive ramp outside, the ramp runs inside the pyramid structure. Think of a hidden corridor that gradually climbs upward within the walls. Blocks could be hauled through that internal path, then positioned outward near the edges as each level is completed. Why do people like this theory? Because it avoids the biggest weakness of giant external ramps. You wouldn't need to build, maintain, and later remove an enormous structure outside the pyramid. The challenge is evidence. Confirming a full internal ramp system without invasive investigation is difficult. So this remains a strong possibility, often discussed as part of a combined approach. Theory number 5 is simple, ancient, and powerful. Levers. A lever is one of the oldest machines in human history. Instead of pulling blocks up a huge ramp, builders could raise them step by step. Picture the pyramid during construction as a series of terraces. A block reaches one ledge, then gets lifted to the next, then the next. Slow, controlled, repeatable. Levers don't require one massive ramp to the top. And when your project is built on repetition, a reliable step-lifting process can be scaled up by organization and manpower. Levers alone probably don't explain everything, but they could have been extremely useful, especially higher up where ramps become harder to manage. Now, here's the detail that can make almost every theory more realistic: friction. Dragging a heavy sled on dry sand is brutal because sand piles up in front of it. But with the right amount of water, the sand becomes stiffer and the sled glides more easily. In a modern lab experiment inspired by ancient techniques, researchers found that with the correct dampness, the pulling force required can be cut roughly in half. Phys.org 4. They also note that wet desert sand can be about twice as stiff as dry sand at the right moisture level. Phys.org 4. And there's historical context too. A well-known tomb painting shows a person pouring water in front of a sledge being pulled, something that looks less like a ritual and more like practical engineering. Phys.org 4. So whether blocks were hauled to a ramp, moved across the plateau, or positioned near the pyramid, managing friction could have saved enormous effort. And here's one of the coolest parts. We actually have written records connected to the project. A set of ancient papyri known as the Diary of Merer describes crews transporting white limestone by boat, limestone associated with the pyramid's outer casing, toward Giza during Khufu's reign. Smithsonian Magazine 5. So we may not have a single blueprint for construction, but we do have real evidence of large-scale logistics, boats, deliveries, schedules, supporting the idea that the pyramid was built through organized systems, not mystery. So what's the most likely answer? Not one perfect method. The Great Pyramid was a long project. The challenges changed as it got taller. Early on, straight ramps could help. In the middle, zigzag or partial spiral ramps could assist. Higher up, internal routes and levers may have mattered more. And across the entire job, friction control, like damp sand and sledges, could make heavy hauling realistic. That's why this pyramid still stands today. Massive, precise, silent. A monument not just to a king, but to engineering. Which theory feels most believable to you? Straight ramp, zigzag ramp, spiral ramp, internal ramp, or levers? Tell me in the comments. And if you want the next episode, we can go inside the Great Pyramid. Hidden passages, strange shafts, and mysteries researchers still debate today. If you enjoyed this video, please like and share. Don't forget to subscribe and turn on the notification bell so you won't miss any new videos. Leave a comment below and let us know what you think.